Here we're picking up with example 7, and this is just an example of a piecewise function in a real application of it. So it says a cell phone company, offers the following plan. So basically you have $80 a month. That's a flat fee, and you get 1,500 voice minutes and so on and so forth. Additional voice time costs 40 cents a minute. So this is a classic piecewise function graph equation, because you have two situations. One, right, when the minutes go from 0 to 1,500, it's one price, and then when they go 1,500 and more, it's a different price. So the way, if you want to write the monthly charges C of t, okay, the way it's going to look is it's $80 as long as t, which is the minutes that you're speaking on the phone, as long as t is between 0 and 1,500 inclusive. So even if you don't talk at all for an entire month, you still have to pay them the $80, right? So it's included there, and 1,500 is included as well. Anytime your T goes past 1,500, you're paying a different amount. So for example, if you talked for 1,505 minutes, okay, what would you pay them? You would pay them the $80 plus, how many minutes have you gone over? 5. So 0.4 times 5. Now, how do you get the 5? It's the amount that you've talked minus the 1,500, right? So that's T minus 1,500. So if you look here, it's $80 plus 40 cents times T minus 1,500. All right? So that's all fine. I mean, that you could have done in Algebra 1. But now, find and state the significance of the following. So if you want C of 754, okay, how much would that be? $80. Now, so what does this stand for? What is the significance? So when it says state the significance, it means, what does C parentheses 754 parentheses mean? Right? What does it mean?
The cost of talking for 754.
Right. So it's the cost, the total cost if you spoke for 754 minutes. And then I would add one more word, is when you say a sentence like this in English, you want to state the correct vocabulary, so like the content, so it's the cost and the minutes, and you also want to provide units, so it's the cost in dollars okay, if you use 754 minutes. Okay. All right, let's move on here. So basically, we have another piecewise function. We want f of -2 and f of 3. So these are two mini problems in one. So first, f of -2. Now, take a look at -2, right? And what you want to do is you want to go here, look at the intervals, and you want to see in which of these intervals does -2 fall. So is it in the first, second, or the third? If it's in the first, right, -2, it's in the interval less than 0. That means you plug -2 into the function for that first interval. So that's just going to be -2, +2. Okay? Now, f of 3 falls in which interval? First, second, or third? Third. In the third interval, what is the function? It's y equals 1, so that's just going to be 1. Okay? Now, let's graph this function. So we're going to call this function 1, 2, and 3. All right, so let's do function 1 first. What you always want to do is you want to plug in the boundary point. Okay, so for function 1, okay, you want to plug in the boundary point, and the boundary point is at 0. So at x equals 0, the y value is how much? 0. Okay? Now, at that point, are we going to have an open or a closed circle? Open. Because it's x is less than 0, not less than or equal to 0. Here. Okay? Now, the equation is y equals negative x. That means it's a line going down with a slope of -1. So you're just going to draw a line with a slope of -1 over there. Okay? Now, I purposely made this so that the second interval is tiny, like it goes from x equals 0 to x equals 1. Because, you know, that's a thing, it can happen, and I don't want that to get in the way. Yeah. Is it going up? We read the function left to right. We read the graph left to right, so it's going down. Yeah, I drew it that way, but yeah, it's negative slope. It's going down, it's decreasing, yes.
Why'd you get the 0, 0?
Okay, so the boundary is at x equals 0, right? So you plug that boundary into the function. 0. Now, let me do the third function first, the blue one. That one is defined when x is greater than 1. Okay? And what does that look like? No, this one. I'm doing this one first. It's just a straight line at y equals 1. And it starts at x equals 1. Is it open or closed at 1? Okay. Now, in the middle there, I'm going to graph function 2. And we're going to plug in our boundaries. So we have two boundaries for function 2, right? The first boundary is x equals what? 0. And the second one? 1. So at x equals 0, what's the value of that second function? 0. And at x equals 1? Now, here, it's 0. Is it open or closed? It's closed. So when open and close overlap, you just fill in the circle. At 1, it's closed. Just fill in the circle. For all intents and purposes, it's a closed circle there. And then in between, it's x squared. That's a parabola. So just make it look like a parabola. Okay? So that's how that's going to work. Okay? Yeah. Okay. This is continuous, yes. I know. Here. Okay, so function 2, right? It exists between x is 0 and x is 1. Yeah? Okay. So its boundaries are x is 0 and x is 1. So you plug in each of those boundaries separately into the function. So first you plug in 0. So at x equals 0, y is 0. Then you plug in 1. At x equals 1, y equals, oh, that should say 1. That should say 1. Okay? Yeah. I had written, mistakenly, I had written 0 there, but I just, yeah.
I understand everything except for why you have a tiny parabola. Like, I don't know how you figured out the parabola.
Well, in that, what is the function for that region?
The parabola in between 0 and 1.
Right. What you care about really is where the bounds are, and then just make it look like a parabola. It can't be a straight line. Just curve it. Okay? All right. Here we're going to go backwards. We're going to write the equation for it. So the way you write it is f of x equals. Okay, now, how many functions are there on this graph? 3. So this is 1, 2, and then 3. So for the first one, That's a linear equation, right? You're going to write a linear equation for it. For a linear equation, what are the two things that you need? You need a slope and a point. You need a slope and a point. In this case, you have a y-intercept, so it's very easy. So what is the slope for this one? 1/2. And you also have the y-intercept for this one, right? What is the y-intercept? 0. So the equation is y equals 1/2 x. So here, I don't write the y equals part. I just write 1/2 x, comma. Now I want to state the interval over which the graph exists. And for that, I want the x's, the x values. So this starts at x equals -2 and goes to 0. So -2 to 0. Now, are they open or closed? They're both closed, so you want to close both of them. We do set builder notation for that one, not interval notation, so we're not going to do the bracket stuff, okay?
So set builder is that.
Yeah. Okay, now let's do the second one. What's the slope there? No. Is the slope 2 though? It's -2. And what's the y-intercept? 2. So the function is, the equation is? So here I put -2x plus 2. And what's the interval?
2 is less than x, and x is less than
Why 2?
or 0.
It goes from 0 to 2. It's open at 0, closed at 2.
No, isn't it the x that's open at 1?
0 to 1. Yeah, it is cool, isn't it? It is pretty cool. The third one is a horizontal line. Slope is 0. What's the equation for it? Y equals -1. So here I just put -1. And what's its boundary? 1 to 3, like this. So, is there anything here? Is there really any new information? No. You've learned how to write equations of line since pre-algebra. So here is one problem where you have to do it 3 times. And the only added thing is the intervals, which really not a big deal. Okay, so let's move on. A publisher requires that printed pages have a length to width ratio of 1.5 to 2.5. Okay? So that's what the ratio has to be always. The minimum allowable length is 7 inches. The maximum allowable length is 11 inches. Okay? So it says write the area of a page A as a function of length L if the ratio is 2.1. Okay? So the ratio, length to width, that's how it's defined, is 2.1. Okay? Now, if it says write A as a function of length, that means it's A of L, A in terms of L. That means in your equation, L is allowed to exist. W is not allowed to exist. That means we need to get rid of W. Now, we have something to go on. We need to get rid of W, okay? But we need, we need to have L in there. So what is W here? Huh? No, this is the ratio. The length to width ratio is 2.1. So W is 2.1. So W is what? L over 2.1. Okay? So now area of L is equal to length times width. So area is equal to the length times the width. So area is equal to L squared over 2.1. Okay, now state the domain of the function. Domain is all of the values that L can take on. Okay, so possible values of L. Well, we are told that the minimum allowable length is 7 and the maximum is 11. So the domain is 7 through 11. Yeah. Now, in the next part B, this, so I have, what is the area of a page A as a function of height H? I mean that to be length L. Right. So now you want the ratio to be 3.2. So W is L over 3.2. Area is L squared over 3.2. And again, the domain is 7 to 11. Here, again, this should be length. It says, find the area of a page with the maximum length and the maximum length to width ratio. So maximum length means it's L is equal to 11. Maximum length to width ratio means L to W is 5.5. Okay, so that means, based on our function there, A is L squared over what? 5.5. And now A of 11 is 121 over 5.5. How much? 22 what? Inches squared. Okay? I didn't make W 5.5. It's, remember, here, W was L over the ratio. And then area was L squared over the ratio. So here too, L squared is over the, it's L squared over the ratio.
Is it supposed to be W equals that?
No, area. Look at this one. Area is L squared over the ratio. Okay. Yeah. I use the pattern. Okay? Alrighty. So now 1.2 talks about graphs and analyzing graphs. So we know that a graph, right, even though sometimes, you know, it might look like a smooth line, really what it is just, you know, points, tiny little points next to each other, right? So I might have a graph that might look like this, but if I zoom in, I would see that, you know, these are really like tiny little points that are connected by that line. Is that right? And each of those points has its own coordinate, right? So for example, this first point here has an x value and a y value. So I can define its coordinate as x comma y. This other point here has an x value and a y value, and I can define its coordinates as x comma y. So really, these have just like infinitely many coordinate points. Now, in the past, we used to define coordinate points as x comma y, because y was y. Now we have another name for y, which is what? F of x. So instead of saying x comma y, the new way to do it now is x comma f of x. And for each x value, how do I figure out what is the f value? What is the value of f of x? What do I do? Well, if I have the graph, I just go up and see where it hits the y-axis, right? Okay, so for example, here, if this is 1, that height there is f of 1. If this is x, that height there is f of x. Okay, so this happens to hit, let's say, a value of 5. Okay, so yeah, f of 1 is equal to 5. But we also know that that means that that distance is equal to 5, right? Okay. So take a look at this. This example. It says use the graph to estimate the indicated function values. Then we're going to conform algebraically. So I've already graphed it for you. And we're just going to do this using the graph. So it wants f of 1. So we go to 1. And the y value there is how much? 1. Okay? So let's see algebraically if that checks out. Algebraically, f of 1, how would you find it? You plug it into that function, so it's 1 squared minus 4 times 1 plus 4. And magically, that's, 1. Okay, so that confirms. Now, let's take a look at f of 3.5 using the graph. So 3.5, 1, 2, 3.5, that's here. And I'm supposed to go up. So it's somewhere over there. So it's about 2, right?
Yeah.
Well, now let's see algebraically what it is. Algebraically, it's 3.5 squared minus 4 times 3.5 plus 4. What would that turn into? What do you guys think? Turns out it's 2.25. Okay? So you see graphically, I mean, it's good enough. You know, it just depends on what precision you're looking for. Okay, let's talk about domain and range. We did it algebraically. Now let's do it graphically. All right, so remember domain and range. So domain is all of the x values for which the graph exists. Range is all of the y values for which the graph exists. What I do is I like to scan my graph. Okay, I pretend, you know, my pen is a scanner and it like shoots out a laser from the top and the bottom. I scan my graph horizontally like this. I scan the x-axis. Every time this hits a graph, it beeps. So here we go. Here, it starts beeping here, right? And then it's going to stop at 4. So between -4 and 4. That means it's -4, comma 4, but it's open on those. Okay? We're going to use interval notation from now on, except in piecewise graphs functions. Okay, the range, we're going to do the same thing, but go, you know, from the bottom up. So this starts at -4, y equals -4, and it stops at 0. So -4, comma 0, is it open or closed at -4? Closed, and at 0, open. All right? It's a lot cleaner to use interval notation. Okay, part B. Domain is the x values for which you can see a graph. So what is this doing on either end? It's expanding like this. So it's going to expand all the way to x equals negative and positive infinity. So the domain is negative infinity to positive infinity. And what about the range? Same. No, we're going to use this notation. Okay, take a look here. Here. All right, so we're going to go from here. Okay, so this is expanding. So we have a graph all the way until 2. at x equals 2, momentarily, there was a hole, there was a gap. And then it picks up again at 2. So right up to 1 point, like 9999999, there was a graph. And then at 2.0000001. So we go from negative infinity to 2, open, union, 2 to infinity. Okay, so take a look again. You cannot do negative to positive infinity. All right? Because you have a graph everywhere until that point 2. At 2, it stops momentarily, and then it picks up again. Yeah.
If the circle was filled in, it would just be negative infinity.
Correct.
With the y value.
Okay, now the range. The range, we start here. There is nothing until you hit y equals what? 1, and then it goes up forever. So it starts at 1 and goes up forever. However, at 1, is there a graph at y equals 1? No. So it's open there. Okay. All right, the next one. You see that closed circle there, that dot? That means the graph does not continue beyond that point. That's an end point. So it starts strictly at -8. We're doing the domain now, the y values. -8 here. Now, we come to this point, even though the x value, sorry, that we're doing the x values. So all the way to 0, we have a graph. Now, at 0, this blue one has an open circle. However, the black has a closed circle, so it compensates for that open circle. All right, so what does that mean? It's beeping, 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 beeping. The beeping continues all the way to 6, continuously. No, so it's -8 to 6, like this. Okay, because there are no breaks in the values where x exists, where the function exists. Okay? Okay, the range starts at y equals what? 0 and goes up to 8, and open or closed? Right. Okay? No, you don't. The end point means it's an end point. It ends.
Oh, so the other one.
Yeah. Okay. Intercepts. So intercepts are where these are points where graph crosses an axis.
So either x or y.
Right. So, let's talk about y-intercept first. This is the y-intercept. It's where the graph crosses the y-axis. At that point, what is the value of x? 0. Now, on the graph, you know where to look. It's where it crosses the y-axis. Algebraically, to find the y-intercept, you have to find f of 0. So you plug in 0 for everywhere you see an x. Okay? Now, x-intercepts, I want to say are more, there's more to discuss there. X-intercepts are where it crosses the x-axis. The graph crosses the x-axis. At those points, what is the y value? Y is equal to 0. Okay? Another way to say it is f of x is equal to 0. Now, so x-intercepts, since this is where y is equal to 0, this is where the function is 0. X-intercepts are also called the zeros of the function, because this is where the function is 0. The function is annihilated at that point. The function is 0 at that point. So how do you find the x-intercept? You take the equation and set it equal to 0. So when you solve it, you get the roots of the equation. So now we have x-intercepts, zeros, roots. Okay? They're also called solutions. So those four terms mean the same thing: solution, root, 0, and x-intercept. To find the zeros of a function, you set the function equal to 0 and solve for the independent variable. All right, so here, I want to do it algebraically first, then confirm graphically. To find the y-intercept, this is where x equals 0, right? We plug in 0. Plug in x equals 0. So it's 0 cubed minus 0. This is equal to 0. And the way you write it is 0, comma 0. Okay? And sure enough, right there is where it crosses the y-axis. Yeah.
You didn't like those kinds of brackets, not like that.
This is a coordinate point.
Okay.
Yeah. Okay, to find the zeros, this is where the function is 0. So f of x is equal to 0. So you take f of x and you set it equal to 0. Well, what is f of x? It's this, and you set it equal to 0. And please, I don't want to give you guys, I don't want to give the same speech about factoring, so let's be careful on how to factor. So x times x squared minus 1 is equal to 0. We can do that here because it's a binomial. So x is 0, x is plus or minus 1. Okay? Now, how are we going to write it? Okay? We can say x is 0 or x is plus or minus 1. We can also say f of 0 is equal to 0, f of 1 is equal to 0, f of negative 1 is equal to 0. For now, keep in mind that there are different ways of writing the same thing. We'll specify later. And you can see that, yes, sure enough, there are 3 points where it hits the y-axis, the x-axis. Okay. All right, here, y-intercept. We're going to plug in 0 again. So it's at negative 3. No. Just put negative 3 comma 0. It's the, oh yeah, y-intercept. Okay, so zeros. We're going to set the function equal to 0 and factor. How does this factor? Right. So x equals negative a half, x equals 3. So we're going to say f of negative a half equals 0. F of 3 is equal to 0. Okay, and this tells me that there is a 0 at x equals 3. That the function is 0 at x equals negative a half. Okay? All right, let's talk about...
Can we write the zeros as like a coordinate?
Yeah.
Like 0
You
and 5.
can, mathematically, it's not wrong. I'm getting you guys used to calculus style notation.
So we need that.
Okay? All right, symmetry. You know there are many functions in math that are symmetric, right? All right, so something could be symmetric with respect to what? Something could be symmetric with respect to the x-axis, meaning when you fold it along the x-axis, the top and the bottom match perfectly. Let's just think about what happens when you do that, okay? Here are 2 coordinate points, right? And let's come up with sample coordinate points there, right? So if the top one, let's say, was x equals 3 and y equals 2, the bottom one is on the same line horizontally, so what would be a sample corner point for the bottom one? 3 comma negative 2, right? So for each symmetric pair of points, the x values are always going to be the same, and the y values are just going to switch sign. Okay? Now take a look at if something was symmetric with respect to the y-axis. Right? If something is symmetric with respect to the y-axis, then with each point, the y value is going to be on the same level, and the x value is just going to switch sign. Now, if something was symmetric around the origin, and you pick 2 symmetric points, then however you go to the first point, so positive 3, positive 4, for the other point, you're going to go negative 3, negative 4. Okay, so negative x and negative y. This is how you can tell if something, so just visually, it's easy to tell where something is symmetric. How about if you wanted to do it algebraically? Well, before we go to the algebra part, let's try to figure it out graphically. So take a look at A over here in example 4. Would you say that's symmetric with respect to the origin, the y-axis, or the x-axis, or none? The x-axis. How about B? Y-axis. How about C? Origin. How about D? You think? It's only y-axis. It's a circle, so you want it to be, you know. Yeah, it's not centered. You want it to be symmetrical around, huh? Origin, yeah. We don't really, yeah. I mean, origin is good enough. Yeah, but you could say all 3. Okay, how do you do it algebraically? Okay. All right, to check with respect to the x-axis, you substitute negative y for y, and you simplify. If, once you simplified and solved for y, if you get the original function back, then it's symmetric. All right? To check if it's symmetric to the y-axis, substitute negative x for x and simplify. If you get the same function back, then it's symmetric. To check with respect to the origin, you do 2 of them, negative y for y and negative x for x, and simplify. Now, if none of these give you the original function back, you're out of luck. It's not symmetric anywhere. So let's do this one. What you're going to do is you're going to split up the portion of the page into 3. And you want to check for symmetry with respect to the x-axis, the y-axis, the origin. Okay? For the x-axis, we substitute, so it's y equals x cubed, right? We substitute negative y. So then you solve for y equals negative x cubed. Did I get back the original function? No, it's a negative, so no. Here, the y-axis, we're going to put in negative x and cube it. So I get y equals negative x cubed. Did I get back the original function? Oh, no. Okay, one more. So negative y is equal to negative x cubed minus y is equal to minus x cubed. So y is equal to x cubed. Did I get back the original function? Yes, so it's symmetric around the origin. You think?
No, because mine was like a plus 3, because I have a minus 3.
Okay. How about even and odd? Okay. Even and odd functions are these. So an even function, let's draw a cute little, what is that?
That's a sine pseudo.
That's a sine function, right? Okay. If I go to x equals pi, what's my y value? At pi, what's the y value? 1. At negative pi, what's the y value? Negative 1. So if you take a plus x-axis and a minus x-axis, the y value will switch sign. Remember that? What about for the cosine? So that's an odd function. For the cosine it's going to stay the same. If I go to positive pi or negative pi, we're going to get the same value. So that's an even function. How do you test? How do you test for even or odd? You substitute negative x and you find f of negative x. If you get the same function back, then it's even. If you get the negative, then it's odd. So if it's odd, each term will switch sign. If none of those happen, then it's odd. Then it's neither. All right, so let's do a couple of these so I could do your homework. So we're just gonna do f of negative x. It's similar. So negative x. Speaking of Descartes' rule, remember when we were doing Descartes' rule, you always had to find f of negative x, and what did we say there? Those that have an even exponent stay the same. Oh yeah, those that have an odd exponent switch sign.
Wow, it's full circle.
Oh my gosh. So now, this is
Oh, look at you.
this is f of negative x. All right. This is f of negative x. Did I get the same function back? No. Did every single term change sign? Not sure where you're going, but I'm still working here. No. So it's neither. Let me repeat that. Hang on. Did we get the exact same function back? No. Did every single term change sign? No. So it's neither. Now, let's take a look at this next one. F of negative x is negative x squared minus 4. F of negative x is x squared minus 4. Did I get the same function back? Yes. So this is even. What do you think C is? Even.
Yeah.
What do you think D is? Okay, f of negative x is 1 over negative x, which is negative 1 over x. Each term changed sign, so it's odd. Let me add another one here. Okay, let me add an f here. F of x is equal to x cubed minus 5x. What's f of negative x? Negative x cubed plus 5x. Did every single term change sign? It's odd. What's this next one? Even. All right, so with that, you can do that homework, plus the ones from yesterday for tomorrow, for Monday.